you have come.
Yes, sir.
I'm there, you are also there.
Yes, sir. Can we begin, sir?
Yeah,
Begin.
Malavika.
Okay, sir. Fantasies are things that cannot happen, and science fiction is about things that can happen. I once again welcome you all to the International Science Fiction Conference. I now request the convener of this conference, Dr. Krishnamurti, sir, Professor of Chemistry, Bangalore University, to introduce Dr. C.S. Sharma, sir, Director, National Assessment and Accreditation Council, Bangalore. Over to you, sir.
Yeah, good morning to all of you. The Honorable Vice Chancellor, sir, and respected speaker of today's session, Dr. S.C. Sharma, sir, and all the audience who are joined to this session. So here it's in order if I want to introduce Dr. Sharma, sir, the biodata is so big and so many things to tell about him. I will just try to introduce in a brief way. So Dr. Sharma, sir, he born in the year 1959. So he is residing in Bangalore at Gandhinagar, and he is one of the few who is ever in pursuit of knowledge and education. He obtained his first engineering degree in BE Mechanical Engineering from Bangalore University in the year 1984. His pursuit continued until 2013 when he last obtained Doctor of Science degree from Sri Chandrasekhara Swami Vishwa Mahavidyalaya, Kanchipuram in 2013. In all, he has 2 engineering and 1 law degrees and 15 doctorates, and including 5 honorary doctorates. He is currently the director of National Assessment and Accreditation Council, NAC, that is situated in the Bangalore University campus. It is a created position in setting the standards of higher education in the country. It gives to his credit that he held 18 positions at university levels, including a faculty position at Institute of Technology, West Virginia University, USA. So he has published more than 250 research articles in reputed journals. He has guided 33 PhDs. He has participated in and involved in 29 research projects, major research projects, and he has involved in several boards. He was the member. He has headed several important boards, committees, and so many things. So if I keep on telling like this, it's a big biodata. It runs to several pages. So by saying all this about Dr. Sharma sir, I take this, I request him to deliver his talk on this occasion of International Science Fiction Conference. So thank you, sir. Welcome you, sir. So before that, I request Honorable Vice Chancellor, sir, to say a few words about it.
Oh, good morning to all of you. We have with us a great and wonderful personality, an academic giant and academic achiever, Professor S.C. Sharma, the director of NAC. I'm indeed very happy and thrilled to listen to his talk today. We in Bangalore University have been conducting this 5th International Science Fiction Conference, and we have invited, a galaxy of speakers from across the world. But we have none other than S.M. Sharma now, very close to our Bangalore University, just a stone throws away. We have indeed very fortunate to have you, sir, and listen to your enlightened lecture. And the topic is science fiction and academics, science fiction and administration, science fiction law. So we have 12 channels running on these 3 days, more than 50 speakers from across the world are addressing in addressing this conference and addressing various topics. And if you see the number of topics we have, and it is voluminous, and it is a great challenge for Krishnamurti to run this 3-day conference. And we are very delighted to have you, sir. And how I can say that our own colleague, very close by to Bangalore University, occupying such a top position, is going to address this August gathering. Let me tell you that Professor Ashi Sharma is one of the in this country, and he is occupying the top position. And if you see the variety of projects or the papers or the type of topics he has chosen, academic topics he has chosen and achieved in his life till now, it is amazing. And I envy him, because after so many degrees and so many branches which he has pursued relentlessly through his life, is a model to any academician in this country. Thank you, Professor Ashi Sharma, for being with us today, and hope to listen to your wonderful lecture, which you will be delivering shortly. Thank you, one and all.
Thank you, sir. Good morning to one and all. Respected Professor Venugopal Ji, Vice Chancellor, Bangalore University, another phenomenal person with great courage and confidence in his life. Before I endeavor into my lecture, I would like to mention Professor Venugopal is a philosopher. He has done his doctorate in the field of economics, that too with a great giant in the field, with Professor K. Venkatagiri Gowdaji, late Professor K. Venkatagiri Gowdaji. And his doctoral degree is from Indian Institute of Science in Computer Science and Engineering. PhD is Doctor of Philosophy. One becomes a philosopher by acquiring the degree and also by the life experience, by the trials and tribulations in one's life we undergo. He is another great, phenomenal person. He has changed the whole scenario of the Bangalore University into an academic sphere and propelling in academics. I had an occasion about 3-4 months back to visit the University Vishveshwaraya College of Engineering, where his heart and passion lies right from his student days. He was there, and then even now he does his research at 7:30, 7:45. When I just barged into his room in the first floor, he was writing a paper and reading a journal. He came out and showed me the progress that has taken place. We should salute, all of us should salute to such a great human being, a great philanthropist. He has virtues, number of virtues. In fact, if I get an opportunity to visit the Bangalore University on some occasion, I think Dr. Krishnamurti ji, you must conduct a workshop or a seminar on Professor Venugopal's contribution of overall sphere as a great human being with different facets, as an administrator, as an academician, as a researcher. And he is the only person in our engineering fraternity who has been elected as IEEE fellow, which is very, very prestigious, and it is not an easy joke. It all depends on the citation index and H index citation and I-10. Sir, with folding hands, I salute you for all your humility and wonders that you have been doing. Thank you very much. Let me start in the name of God. My lecture, Professor Kulos, Nobel Laureate in Physics, Dr. Ji Krishnamurti, Professor, Department of Studies in Chemistry, Bangalore University, registrars, directors, deans, professors, academic administrators, teaching fraternity, ladies and gentlemen. It is a matter of pride to deliver this special talk on this occasion and address the wonderful and august gathering through the digital platform. Today, I would like to delve on a topic, science fiction in ancient Hindu thoughts. and the need for ethical perspectives. Science fiction in ancient Hindu thoughts and need for ethical perspective. Whenever we encounter a new experience, there are possibilities that we fall back on our common sense. What is this? Fall back on our common sense. But this is not true in case of social activities which are regulated and controlled by science. However, prior to any invention, they are termed as only fictions in our life. But when they are invented and implemented in our activities, they become a part of our life. In our scriptures, we have different type of siddhis, what is called as anima siddhi, garima siddhi, mahima siddhis. Shankaracharya, in one of the most magnum opus work of Saundarya Lahari, he says, Shruti Smriti Purananam Alayam Karunalayam Namami Bhagavat Padam Shankaram Loka Shankaram. There, Anima Siddhi is just a small atom. Mahima Siddhi, a big atom, biggest form, which takes a biggest form. These are all Siddhis. Here we can classify into two structures. One is called as Gochara. Gochara means that which can be seen. Agochara is that which can be felt. For example, Gochara, you can see the materialistic objects in front of your eyes. That is Gochara. And Agochara is, for example, let me take the example of a medical sciences where a person is undergoing depression. He cannot express, his actions are different and his thoughts are different. Therefore, what happens? And the opposite person will not know what kind of depression he is undergoing. This is a very, very important thing. This is agochara. Similarly, one can feel in Ramakrishna ashram or any other place when you go and sit and do the dhyana, you will feel in your body the reverberations of positivity, and that is a continuous process of tapasya. This is called as agochara. Agochara is what is that which you can anubhava, which you can feel. During 18th and 19th century, when the concept of car was just pure imagination, purely an imagination, who ever thought this automobile industry would flourish so much? It was just a pure imagination. It evolved from scientific fiction. Today, the cars and other human driven vehicles are going to change dramatically in the coming years. Why? Predominantly in the way they are driven. Therefore, there may be a trend away from human driven autonomous vehicles that will have a momentous impact on our lives and society. We should underline the term. It will have a momentous impact on our lives and society. Traffic regulated by robo technology that could detect people in order to avoid accidents are already adopted in our lifestyles. Robots are such a pick and place robo, flexible robots. There are so many robots which have come. Whoever imagined in the 17th, 18th century? Today, we are witnessing surge in scientific research and development as never before. However, mere development will drain our environment. Mere development will drain our environment. For example, we have had lot of road repairs, etc., in India and in Bangalore. But at least, if you had a footpath where the water could percolate, the environmental conditions would have, the groundwater would have increased, etc. Ecology and planet, and hence we are imagining of tomorrow by fictionalizing day after tomorrow, and that the development should satiate not only our present needs, but it should fulfill the needs of our progeny without compromising their needs. When we talk about imagining of tomorrow by fictionalizing the day after tomorrow, for example, a person astronaut goes and lands on the moon. Now, in the mythology, or in the astrology, we say that the planetary conditions, Chandra, moon, if when a person goes on the moon, that aspect is quite different from the astrological Chandram Bhajamanasa. There is a very nice Kirtana of Muthuswami Dikshitar, which blends the scientific aspect, fictionalizing aspect also. The concept of magical objects have existed since antiquity. Since antiquity, in our childhood, we have read stories where magical brooms sweeping the floor in fairy tales, magic mirrors in Snow White, which responds to the witch, have occupied our fantasies. Today, our reality in the form of robot sweepers, internet driven mobile phones responding to voice questions, while many things which are pure fantasies of yesterday, with the power of human wisdom and scientific reasoning, have become tomorrow's reality. What is a fiction today is tomorrow's reality. With increasing power of supercomputers, invisible strings are connected to control our activities, to whom we have surrendered our every aspect of our personal data, and are optimistic to see a great future of technology which defines and foretells our physical requirements, biological needs, mental capacities, including longevity. For example, our new education policy says it should be technology driven at every stage of the policy, technology driven, and which becomes a reality, and the total effect will be seen by 2040. Our smart cities are creating senior citizens, and those days are not too far where our entire social and civil responsibilities are connected to our biological sensors. What a nice development, please imagine. Even in our epics, Ramayana and Mahabharata, alongside religious aspects, it revolves around human values, law and order, and also mesmerizing universe and its vast creations, which are even today amazing impossibilities, and science stands as scientific fiction in our times. Be it civil concept of civil engineering or mechanical engineering or aerospace or physics or chemistry, you find every aspect in the Ramayana and Mahabharata, which I would like to delineate now further. I would like to quote few instances taken from Ramayana and Mahabharata. In Ramayana, Sundarakanda, the description of a particular zone in Indian Ocean controlled by demon Simhika, which is similar to Bermuda Triangle. The Bermuda Triangle. Pushpaka Vimana possessed by Ravana has become today's reality during our times. The story King Kukudmi, when he visits Brahmaloka to find a suitable groom to his daughter, wherein he waits for few minutes. And after meeting Lord Brahma, when he returns to earth, realizes that he has surpassed the time equal to eons. Many, apart from the story of Markandeya Rishi, during his routine oblation experiences, the Mahapralaya or Great Deluge, and these depicts the past and futuristic time travel concepts. You see, the concept of Desha and Kala are very important. Time and space, Desha and Kala. Muthuswami Dikshitar, in one of the kritis called as Panchashat Pita Rupini, he says, Desha Kala Pravruddhini Mahadeva Manollasini, Desha and Kala, time travel concepts, voyages to other lokas or planets located in some other galaxies, interstellar contacts, creation of supranatural hybrid species, which Narasimha is the avatar of Narasimha, supranatural hybrid species of a lion as well as human. Hanuman, Ganesha, etc. And those fictions of science are yet to be achieved in reality. The story of Bhasmasura may be equated with Frankenstein or the modern Prometheus, authored by Mary Shelley during 19th century, which is considered as first science fiction of modern times. Even in modern era persists, attempts are being made like voyage to Mars and other search of human habitat, interstellar expeditions, creation of new species of animals like liger, pegon, pumapard, wolpine, etc. So many species. And when we achieve time travel concept, probably our past may become our future. Present may become past. And in such case, future will be non-existent. What a nice statement. Our past may become our future. Present may become past. And in such case, future will become non-existent. Shankaracharya in his Bhajagovindam composition very nicely, subtle philosophical trace has been has told in his past may become future. It's a cycle. Punarapi jananam, punarapi maranam, punarapi janani, jatare shayanam. Iha sansare baudastare, kripaya pare, pahi murare, govindam bhaja mudamate. What is our past? What is our future? It's a cycle. It goes on and on and on. It is surge of the human mind which keeps on exploring the possibilities and expanding. What is it that we expand? The realm of imagination into fiction, imagination into fiction, and fiction into becomes reality. For his ephemeral benefits, imagination into fiction, fiction into reality. This is such a wonderful thing. Even in Bhagavad Gita also, at every stage it says imagination. You imagine, it brings into fiction, and fiction into reality. During this process of imagination to reality, we have the science behind it. This science will realize into reality. However, in this uncertain world, anischaya, in this uncertain world, any invention will not sustain for longer unless it has true ethical justification and accountable assertions, which are very important, within the purview of well-defined responsibility. It doesn't mean that we have to halt the imagination and material progress fueled by fictionalized science. We don't have to halt, we don't have to put a brake, and the material progress fueled by fictionalized science. But at the same time, man should be wise enough while he engages himself with experimentation, which is very important. One best ethical instances I would like to mention here is about Jagat Guru Adi Shankaracharya was 6th century AD, wherein he experiments the act of Parkaya Pravesha. Parkaya Pravesha, that is his soul out of his body and entering into another dead body. Here, these are all Siddhis, I said, Animadi Siddhi, in one of the compositions of Muthuswami Dikshitar. Animadi Siddhi Ashtaishwarya Pradham, Animadi Siddhi. Like this, even in Lalita Sahasranama or Saundarya Lahari also, there the concept of benign and benign form of Devi and the Nijaswarupa Devi is depicted, and even in certain parts of Kerala this is being practiced even now. There Adi Shankaracharya performs this act only. I'm just mentioning very carefully, I'm talking only in the quest of knowledge and to gain experience to Jivatma, but through another medium or body. This Parkaya Pravesha is through another medium or body. This is a Siddhi. In the process, he piously observes the purity of his soul, mind, and body. Purity of soul, mind, and body. However, the act of Parkaya Pravesha even today appears to be fiction and beyond the perception of modern science, yet it was a reality attained by Adi Shankaracharya. In fact, in Atma Shatkam, he says, Nacha Shrotra Jihva, Nacha Gatra Netram, Nacha Vyoma Bhumir, Natejo Navayuhu, Chidananda Rupahat Shivoham Shivoham. I am not the mind, the intellect, the ego, or the memory. I am not the ears, the skin, the nose, or the eyes. I am not space, not earth, water, or Panchabhutas. I am the form of consciousness and bliss. I am the eternal Shiva, Chidananda Rupa, Shivoham, Shivoham. Aham prana sangyo na vai panchavayu na va saptadhatur na va panchakosha na vatmani padau na chopastapayo chidananda rupa shivoham shivoham. I am not the breath, not the five elements, that is the Panchabhuta. I am not matter, nor the five sheets of consciousness, nor I am the speech, the hands, or the feet. I am the form of consciousness and bliss. I am the eternal Shiva. So you know, in this particular shloka, it very nicely depicts the realities. We should be aware in adapting our ethical philosophies at the pace of dynamism of scientific thought. Social accountability, both individual and societal nature, is one of the major factors while conducting research experiments for imaginations of human mind. It should yield fruitful results for the noble cause of the society, and anticipated results should justify the performance of experiments. This is important. Prior to an experimentation, there should be reason to believe, and criteria of humanitarian importance should never be ignored. This is the most important aspect of it. The humanitarian importance, whether it is a imagination, imagination, reality. But ultimately, when the science factor comes in, the humanitarian importance should never be ignored. Otherwise, either it may create doomsday for man, or collapse of man before Mother Earth, Mother Nature. I once again thank the authorities, especially Professor Venugopal ji, Professor Krishnamurti, all the organizers of Bangalore University, and the organizers of this event for inviting me to share my thoughts with you. I think I cannot talk further. All my whatever I had prepared is exhausted. This is all what I can talk about this. Well, if it can go on and on. For example, Newton's third law also can be related to fiction, and entropy, concept of entropy in thermodynamics can be related to fiction. Concept of heat and mass transfer in thermal engineering can be correlated to fiction and reality. Similarly, elasticity and plasticity concept in machine design and material science also can be correlated to imagination, fiction, and reality. It can go on and on. I'm immensely grateful to all the authorities to have given me this chance. Whatever little I could, I have done. Thank you very much. Namaskara. Thank you.
Thank you for this enlightening session, sir. If there are any questions by the participants, please leave it in the chat box or unmute yourself and ask directly. If there are any questions, please leave it in the chat box. On behalf of Bangalore University, sir, I thank you once again for taking your valuable time and giving us this wonderful lecture. Thank you, sir.
Namaste. Thank you very much.
Our next speaker is Dr. Annapurni Madam, and I now request Professor Vijay Kumar H. Dodmani, sir, Head of the Department Physics, Bangalore University, to kindly introduce Madam. Over to you, sir. Sir, please unmute yourself. Sir, please unmute yourself. Yes, sir.
Okay, thank you. So, good morning to you all. So, it's my proud privilege to introduce Professor Annapurni Subramaniam Madam, Director of Indian Institute of Astrophysics. Professor Annapurni Subramaniam is currently the Director of Indian Institute of Astrophysics, Bangalore. She has about 30 decades of research experience and has published more than 150 research publications in topics such as star clusters, stellar populations, galaxies, and ultraviolet astronomy. She has guided a large number of students, and 10 have completed under PhD under her guidance, and she has importantly involved in 2 major national projects. She is the calibration scientist for the UV imaging telescope, UVIT, on board India's first space observatory called as AstroSat. She has compiled and predicted its performances before the launch, planned and completed the calibration after its launch. She has also developed a mandatory user tool for safe observations of the telescope. She was heading the Indian team of the observatory software 19 for the 30-meter telescope, which is being built by an international consortia of the nation's agencies, research agencies, with India as one of the partners. She has issued many awards, to mention only a few. She is the Fellow of the Indian Academy of Sciences, Fellow of National Academy of Sciences, and life member of the International Astronomical Union and Astronomical Society of India. She is Cowley Fellow instituted by Cowley Foundation and National Advances of Sciences USA, and she is the recipient of C.V. Raman Young Scientist Award for Physical Sciences from the Government of Karnataka in the year 2018. There are so many credentials to the madam. So, Professor Annapurni Madam, Observatory, AstroScience, AstroSat, which has been there successfully in space, performing to its all planned and predicted level. As it's there since over past 5 years. I request Madam to deliver her talk on AstroSat.
Hello, good morning. I guess I'm heard.
Yes, ma'am, you're audible.
I'm just sharing my screen. I'm making it full screen now. Is it, you can see my screen, I guess.
Yes, ma'am.
Sorry. Um, so I'm going to talk about astronomy and astrosat, and um, um, uh, befitting to the topic of this conference, sky has been the main topic of mini science fiction. And from day one, people started looking at the sky, the dreams about going into space and dreams about what we do there and dreams about extraterrestrial life and life outside in other planets, galaxies, etc., have leashed out the enormous amount of fiction connected to space. So um, the other aspect of it is when you actually get to do it, how do we do it? So how do you connect your aspirations and dreams by looking at the sky? When will I reach to the stars? And literally, how do you convert that into your practical engineering projects and endeavors? So in that, India has also done a very good job of launching satellites, and also now we have launched our own astronomical observatory, and which takes pictures of the sky above the atmosphere. So I just wanted to start with this picture of the sky, where you get to see various things projected onto the sky, which is the celestial sphere. So you get to see this our own galaxy, Milky Way, the nearest one being the within our solar system, comet, and the nearby galaxy. So everything gets projected, and your dreams and your um, thinking about what you can do kind of cuts across various distances and various types of objects, which are all present over there. Going to the next slide, now people also go to remote places to take astrophotography. And this is one such picture taken by Doje Angchuk from our Hanley Observatory. You can see the huge reptile kind of a pattern here, which is created by our own galaxy. And then the dark patches out there are by due to the molecular clouds, the molecular hydrogen, which is absorbing the light by casting a shadow. So various things out there, and the bright knots on those dark clumps are the places where the young stars form in our galaxy. So this has been a new trend in getting beautiful pictures, which actually increases our curiosity about the space and its contents. Now, astronomy is one of the ancient topics, but we also have backed um, Nobel Prize in physics. And this is the recent one where the Nobel Prize was awarded to uh, discovery of compact objects and black holes this year. So Roger Penrose got for the discovery that black hole formation is a robust prediction of the general theory of relativity, and the other half was shared by Gensel and Guess for the discovery of a supermassive compact object at the center of our galaxy. So the fiction of objects like black holes are converted to in theoretical physics, as well as detections of something which is similar or which appears to be like a black hole has already been done. So they completed 15 years of tracking the trajectory of stars nearby such a system, which is there at the center of our galaxy. So thinking about things like that and converting into actual in science, explain it in terms of science, and also taking data, making instruments and observing them and taking data and showing that yes, something similar to that is over there. So this has captured the attract um, uh, eh, the people who gave the Nobel Prize and is also awarded there. So that is complete conversion, or rather closing the loop of imagination to actual science and converting in and getting recognition for that. And why do we do astronomy? Astronomy is one of the ancient sciences, and the humans have looked up the sky for their own well-being and also their own advancement. Now, the major requirement in very old days, when you didn't have a wristwatch to look into for your time, and also your mobile to tell you the GPS and give you the direction, you had to look at the sky and look at the stars. You need to know your stars. You need to understand which stars appear in the sky during which part of the year, and how do they, where do they rise, where do they set. So when you set out to walk from the temple to back to your home, or from your friend's house in one village to another village, you need to get the direction. And the directions are given by identifying the stars, rising stars and setting stars, etc., and giving you direction which way you need to go, where is north, where is south, etc. And the time tells you this star is supposedly here right now, or for that matter even the evening moon, or the moon is in the west, or the moon is in the east. So today it is supposed to be there, so it must be early part of the night. I have some time before I reach home before midnight. So it is very important to understand which objects come at which time in the sky. It used to be very, very important. It's one of the life skills people had to have to survive. But what is the status now? You do not need to look at the sky. I don't think anyone steps out and looks at the sky to see whether where are the stars, or even there's a moon, etc. That days are gone, because we have outsourced those requirements to technology. Now, how does that happen? So, is astronomy still relevant? Has the technology taken over completely that you don't want to know what the stars are out there? Your life is not dependent on them. Is it that case? Not quite, because you might even look at this watch to get the time, and may not. You don't need to actually look at the stars or the sun. But in general, if you get up and really look out of the window to see, oh, it's already morning or it's already evening. So in the total sense, you still look at the sky or look at outside and decide whether it is what part of the day it is. But how about directions? Of course, you use the GPS. You don't look up at the sky. You look into your mobile and put the map and say that, okay, put the location and this is how it goes. Now, how does that work? The GPS works by triangulation method, where you sit on this, your location is identified by a constellation of satellites which are orbiting, and then two of them kind of position you, and triangulation method is used to position you. Now, you should remember that these constellations of satellites are not stationary. They are moving, they are orbiting the Earth. So they are not stationary. At any point of time, they need to locate themselves. Now, is the Earth stationary? No, Earth is moving with respect to the sun throughout the year. So it goes around orbit, in orbit. And is the sun stationary over a time scale? No, it is not it's stationary. It goes around the center of the galaxy. So in very, very large time scales, our galaxy is also moving. So in principle, everything is moving, nothing is stationary. So if you are planning to locate yourself with something which is moving, they need to find out where they are first, right? So how is that happening? So the GPS uh, needs something which is very stationary, a stationary framework to identify themselves and locate themselves with respect to that framework. And that framework is given by a set of quasars. Quasars are very bright radio sources, but they emit in the optical as well. They're very bright and they appear to be like stars, but then they're very far away and we can detect them. So astronomers suggest which are the quasars, and we know how astronomers know how to differentiate a star from a quasars, and then identify them, and they are given to as a frame of reference to the GPS. So in a nutshell, we have outsourced this job of looking at the sky to something that is the GPS satellites, which in turn look at these quasars. So you still need astronomers and astronomy to tell you where to look at and how to create a framework. So without which it is not possible. Now, if you take this fictional thing of interplanetary space mission or going outside our solar system, you need guidance, and guidance can be provided only by the astronomy and astronomical sources. So it's still, astronomy is still relevant for our science and our day-to-day life, in fact, and of course our endeavors. So astronomy has brought in a lot of technology and to our society, which people used to think 50 years back, how can you actually make a phone call? Do you actually will be, I mean, in those days the telephone used to be sitting in one corner and you need to go and pick it up and wired, etc., right? Now things have changed, and now many of this communication, mobile communication cameras and the image processing, computer languages, etc., come a lot from astronomy, because astronomy pushes various requirements, the dreams which the astronomers have to look at the sky and look at things differently, actually push the technology sector to an area which is not comfortable, and that brings about a lot of innovations and incredible advantage to the society. Many of this can be looked at, found in the International Astronomical Union website. Now, what do we do in our institute? Just to give you a couple of minutes on that. So, the Indian Institute of Astrophysics has its headquarters in the Koramangala campus, and we have these many field stations. Most of them are located in the south. Our oldest one being the Kodaikanal Observatory, which has been collecting data of the sun for the more than 100 years. It's actually 120 years. So, if you wants to study the long-term variation of energetic particles coming out of the sun, or the butterfly diagrams or the coronal mass ejections, one can look at this data. This data is publicly available in our one of the portals, and you can and the observations are still continuing as well. We have Vainu Observatory, which is completed for 50 years, which is near Vellore in Tamil Nadu, and that also has a lot of telescopes which look into the sky and look at stars and other objects. We have an outside Bangalore campus at Hoskote, where we have a space sciences lab and also a remote facility to control all the telescopes which are located in Leh. So we have a field station there, and also there is a Gauri Bidanur observatory to look at radio emission from the sun. On top of that, we also have a satellite, that is AstroSat, up in the space. The UV imaging telescope is built in, and it is led by the Indian Institute of Astrophysics in collaboration with other institutions in the country. This was launched in 2015. It's completed 5 years its operation, and its payload operation center is actually over here. So we actually do the data processing from the campus out here. So just give you a few pictures. This is our Hanle campus, bright blue sky, the 2-meter another telescope out here. This is a green observatory with solar power. This is a Hoskote campus where it is the dish is over here. So astronomers go there to take data or conduct their experiments. And this is remotely operated from here. This is a Kavalur observatory, green observatory. I mean, actually, literally, you can see the trees out there. And then these are the telescope out there. This is the AstroSat, which is being integrated. The UVIT is out here. This is the Kodaikanal tunnel telescope. And this is the dipole array in Gauri Bidanur. Now, going forward, there are these the universe forms, the stars are formed in the universe, and they die and they form in groups. So astronomers study these kind of systems, and they create telescopes and detectors. Telescopes collect the data, collect the photons, and the detectors record them, and then you have the computer processing to create images and show it like this, and also do science with it. So that's what we do. And we also have a cutoff from the atmosphere, where if you are looking at outer space, the environment in the outer space is very different, because the air, the actual electromagnetic radiation which surpasses the outer atmosphere and reaches onto the ground is very different. Many of the rays are stopped by the ozone layer, and if you want to collect those high energy radiation and study them, you need to go above the atmosphere. The long wavelength, also the good amount of water vapor in the atmosphere stops them. So this is the transmittance of various radiation because of the atmosphere. So when one has to launch a telescope or a mission or Even putting people outside this atmosphere, one has to take care, because the conditions out there is not same as the condition within the atmosphere. So why should we study all this? Because we know that this is something which everybody knows. You would have come across these at some point in time in your life. That is the periodic table. And this is already 150 years now. And the question rises, where did you create all these elements? We all know that it is not easy to create an element on a tabletop. So what is requires is that the nuclei, if you want to bring in two elements together or two atoms together, first you need to get out there, take out the electrons, and they make it a nuclei. And if the nuclei is there, they are positively charged, so the Coulomb repulsion doesn't bring it together. You need extreme amount of force to bring them together, and that normally happens at very high temperatures. So the stars, which are basically gas, plasma, ball of plasma around, so these are live nuclear reactors. And you know that the surface temperature of the sun is about 5,500. That is the surface temperature. But if you go inside, the temperature increases very drastically to up to 1,000,000 degrees at the center. And now what happens at the 1,000,000 degrees is it is able to bring four hydrogen to become one helium. So that is how it creates a helium at that temperature. Now, in the early Big Bang, the universe is the most abundant element, 75% is hydrogen. Now, very, very small fractions of other elements are present in the universe. Who created it? How it is created? We now know that the various types of stars which were there before the sun was formed created all these. And this is thanks to spectroscopy of stars, and also understanding how atomic and molecular spectroscopy from our own laboratory combined together, we are able to decipher this. And so most of the elements shown out here are either produced in large stars, in supernovae, and small stars. You can see that only very small are man-made. So we are indeed formed from stardust. And this is the whole table describes you from where, which part of the element comes from which type of stars. We also know what reactions are responsible for this, thanks to various types of studies. Now, how are they formed? So when you look at very big stars, sun is a very small star, in fact, and we scale other stars with respect to the mass of single sun. So if you're looking at stars which are more than 8 times the mass of the sun, what happens is they start off their life with hydrogen converting into helium by a fusion reaction in the center. But when the star evolves, because the center gets hotter and hotter, and you have more and more higher elements in the center, the temperature is hot enough to fuse helium to carbon, carbon to silicon, magnesium, neon, and then finally to iron. So you can imagine the later last stages of this high mass star before it explodes into a supernovae as an onion. Is like an onion. So onions in skin, where each skin represents each element. So it has produced all these elements, and then when it explodes like a supernovae, I'm sure many of you have heard at some point of the or the other regarding the supernova explosions. They're very highly energetic explosions. It's basically an implosion of this iron core, which releases huge amount of energy, which makes the outer layers explode, and in the process you can see how many elements are being thrown out into the surrounding medium. Now that is the pollutant. Now so this pollutant, the next generation of stars formed from this material will have a little extra of this carbon, nitrogen, magnesium, etc. So that is how we understand the formation of these elements. Now, India did dream of having an astronomy mission for a very long time, and the requirement was put together basically to understand many of these systems, like hot objects like supernovae. The last stages of stars emit a lot of high energy radiation. Also these, I mean, the picture shows a black hole with a jet, etc. And now the matter, you can't see it, but you can detect the jet or the matter which is encircling it, the accretion disk. And X-rays are highly suitable to detect and study these systems. the important thing is these are very, very transient systems, and many exotic phenomena happen in a very short period of time. So if you want to study everything together, then you can't say that I will first look at it in X-ray. After then the detector goes off, then you actually look at it in ultraviolet. Then after that you do it in visible. Now this time spirit and the time span by you complete your experiment, the property of the object would have changed. So this is not simultaneous. So the ideal thing would be to look at the object simultaneously so that you can actually see what is actually going on out there. Um, why you have to do that? Because the production of a particular photon with a particular energy tells you what is the physical phenomena that is responsible for producing that. Okay, that is the main reason. So the requirement was to look at it simultaneously. So the concept of astrosat was looking at the sky simultaneously in the multi-wavelength, starting from hard X-ray to visible. Now X-ray payloads were many, and one was the UV and visual payload, that is the UVIT. Now this was long. You can see that is a massive payload, and it has got a lot of detectors, a lot of operations. It's a complex in terms of technology, complex in terms of number of detectors on board, and you also need a huge amount of electronics to operate it. As I said, the condition out there is not very friendly. It's a very hard condition because a lot of charged particles fly around, high energy photons fly around, which can harm the electronics. Electronics is a very, very critical component out there for operations. And of course, you need to command the whole thing to do what it should do. And after everything, you need to get back all the data down to find out what is actually happening out there. You can't just check out, go there and check it saying that, okay, this is not working, let me fix it. So that's not possible. So if something is not behaving properly, all that you need is you need relevant information which is brought down so that you can find out, troubleshoot, and take the corrective steps. So you need something called metadata, the health status of all these things, along with your science data. So it's not only commanding, which is uploaded, the downlink also has a lot of data, not only your science data, but a lot of metadata. So all these operations are quite complex, and that way it is quite unique because it's quite massive. So this project was dreamt quite a bit long back, and then realization from the concept probably took about a decade and a half or more than that, almost 2 decades. And actual work started a decade before the launch. So it is a very, very long process. And eventually everything happened and put together, huge teams involved and worked together, and all this was put together and launched on 28th September 2015. It's at a 250-kilometer near equatorial orbit, and it has been functioning very well, and it's completed 5 years. So that is an excellent milestone to showcase that yes, we can dream, and we can actually convert that dream into a reality, and then make the reality happen and continue to perform. So that is the lesson we have learned. And what is UVIT? UVIT, of course, when you talk about a telescope, I think most of us think of two things, either a tube or a dish, or the antenna like a dish. Okay. So in this case, it's a tube because you need to hold elements like mirrors together, and you need a tube to hold them. And then you take the image using the camera, which is actually at the other end. And one has one camera, the other side has 2 cameras. And this is the actual integrated things. The complexity out here is that the that the UV photons don't reach the ground because the molecules up in the atmosphere absorb them. Similarly, when you actually create such an instrument in your own laboratory, if you happen to have a molecule in the tube, then the UV detection, your test will not happen. The detector will not even detect the photon because intervening molecule will absorb it. So that means your lab has to be molecular contamination free. So the Institute of Astrophysics set up a lab, a very specific lab, clean room facility in our Hosokote campus, particularly for this. And people have to be trained to use this. You can, this is the one of the setup where on the optical bench it is integrated. People where contamination control is extremely important. This is one of the, this is the MGK Menon Space Sciences lab here. Here people use masks, PPE already, and we can see how difficult it is to day in and day out you have to wear, because if you want to enter the lab and work, you have to use it. And the contaminations have to be controlled not on daily basis, not for 1 or 2 weeks, but for years together. So strict adherence to protocols is extremely important to deliver something which is so sophisticated and make it work. This is another place where these are the clean room things. So this is the 2 tubes, and you can also see something's getting wired out there. This is for thermal stability. So you can say that when the it is orbiting the Earth, it might go towards the sun and away from the sun, right? So onto the night side and the day side. So the temperature, there is a large amount of temperature variation. None of the things should malfunction. It should actually function extremely uh, um, um, in a very in the same manner. It shouldn't, you wouldn't be knowing whether it went through thermal cycles or not. So stability is extremely important. So you can see people working there, and this is actually the outer case for it, and this is the thing which connects to the main bus, the shuttle. And this is the other behind of the thing. And you also can see that if you are creating an instrument which is a tabletop to be deployed either in your lab or in your backyard observatory or in a ground-based observatory, you just take it carefully, put it up, hook it up, and test it. If some component fails, take it down, fix it, put it up. But that's not happening in Space Telescope. Once it is launched, it is only up there. And now launched. Launching has a lot of things. There's a lot of shaking happens while the rocket is going up. So all this shaking, none of this shaking should break any of the components. So right from the design, it has to be, it has to withstand all these launch loads. So you have to test all the component level as well as the integrated payload level vibration mechanism. So the shake and bake tests are very important. So this is the shake test. This is the vibration platform, and the 2 tubes are sitting out there with everything together. So your mirror should not break, your filter should not break, your cable should not break, your detector should not break. So you have to make sure that none of them break. And thermal cycles are very important. So that is the shake and bake. So baking is important. None of them should show any deterioration after thermal cycles. So this is as I said, these sometimes something breaks. So what happens? So it goes back, makes it redesign, re-engineer, remade it, and retest it. So review processes and stringent criteria for completing and validating processes are very important. So reviews and making sure that you have ticked off one particular item. Yes, you have manufactured and it actually fits all the requirements and specifications is very important, and this is done by several types of reviews. So this is the payload we started off with. This is the thing which is completed, and now this was integrated into the entire Astrosat, and this is ready for launch. It was launched on the PSLV-C30 of Astrosat. You can also see that this is people are wearing PPEs, and also this is not in COVID times you're wearing it for your protection, but here you are wearing it for the protection of the instrument. And you can see this blue tube coming out of the UVIT2 tubes. This is the dry nitrogen being flushed to make sure that there are no molecules. You just flush out the air, which is, even if you have a molecular contamination, it is flushed out. So that is how it is done. It is done till the launch takes place. And this is the launch. And this is one of the earlier images of the Galaxy NGC 2336. If you take on one orbit, okay, I should also say that this completes one period in 90 minutes. So it goes over Bangalore once in every 90 minutes. So you can see the speed with which it moves. But it also, what it has to do is that during the night time, when the dark part of the sky, it has to point to one place and take a picture. It is moving and pointing to one direction and taking a picture. Obviously, there will be drifts, there will be shakes. So this is the eventual picture you get. But offline, we can process it and you can do the de-drifting and remove the signature. And once you do this, this is the picture of this particular galaxy, and the galaxy which is shown at the center, which is actually, you can't see it as a galaxy because these signatures have erased all its features. When you do the de-drifting and all the corrections, you get this picture. And we were so happy to see it because the same galaxy which was observed earlier by Galax had this particular resolution. Now you can clearly see that the resolve the Indian telescope has achieved when compared to the US mission. So it is very, very clear now. The last 5 years, many science cases which was pursued by the Galaxy UV mission has been much, much improved and resolved, and better results are coming out of the study now. We just finished a conference on UV science studies, and that is the completion of 5 years of UVIT. Last week, several new results and interesting results were presented. This is another picture taken. I mean, I should also warn you that in the idea of making people more attracted, and I mean presentation wise, astronomers create false color images. Please be aware that these are false color images. They're not true color images, in the sense that this is the color given by the producer of this particular image. Like I decide to give red color to the one of the filters and blue color to the UV. Obviously, the ultraviolet you cannot see it, right? So you detect it through a mechanism, and then in order to represent it, to make you how I see it, I give it a color. So you should always see that when somebody is giving a color to a UV or an X-ray image, it is the perception. You want to convey that it is how it looks. So this is a false color image of a galaxy falling into a group of galaxies, and the material is stripped and still the new stars are being formed. So this is one of many studies are centered around these galaxies, which are named as jellyfish. And these are groups of stars, which these are coming from my studies, and I'm looking at studying the last stages of sun-like stars, how they die, and what kinds of chemistry do they have, or what is the contribution to our chemical evolution by these stars. So yeah, I stop here. Thank you.
Ma'am, Vijay Kumar sir has a question actually.
Yeah, I can see it in the chat.
Yes, ma'am. I understand NUV filter is not working. Please explain the same.
Yeah, so around 2018, I think it's March, we lost the working of NUV detector. As I said, the space environment is not very safe. So you do get a lot of charged particles. And another thing is that we get rid of this extra charged particles by grounding the electronics, right? So you are safe because the extra charges flows into the ground. There's no concept of grounding there. Of course, you can create a Faraday cage or protection mechanisms for the detectors, but still you do get some static charge, and once the static charge starts developing, the electronics start misbehaving. So once in a while we have to actually reboot these the electronics to drain off the charge and start all over again. So that's a protocol to be done. In one such operations, due to some issues, the electronics did not behave well and the NUV could not be restarted. So we tried a few times, and then it did restart, and then it functioned for a couple of months, and then again went into this problem. So we tried for several times, several types of interventions, but NUV channel could not be. The detector is safe, but then it's not powering on. So we could not save that. But we have been starting whenever we find problems with the far UV or the visual channel, we have been restarting it. We haven't had any issues till now with that. Yeah.
Madam, can you hear me, madam?
Yeah, yeah.
Yeah, that NGC2336, there was the third image also in the panel. Yeah, this one.
This is the ground-based image.
Okay.
This is a ground-based image, yeah. So here what basically will happen is like ground-based image is from the optical, actually. It's an optical ground image. You can see that the central bulge of the galaxy, you can see a slight of a extended bar type of a feature. Now that is completely disappearing in the UV. You see a very, very nice thin spot. So that basically tells you that these light is coming from older population where sun-like stars which do not have much emission in the UV.
Yeah, I
So
was
you
not
can,
clear that
yeah,
it
you
is
can,
optical and UV.
this
I
is
was not
optical.
able to figure out. Yeah.
Yeah, this is optical and that is the UV. So you can, it basically tells you where exactly the new stars are formed.
Madam, this spectroscopy is possible. I understand lower resolution spectroscopy is possible.
Yeah,
UV spectroscopy.
yeah. So in this, let me tell you, maybe I'll
AGN.
take the, yeah. So if you take one such image like this is actually a color composite, you will, this is the proper UV image where only UV photons are detected. We did not combine it with optical. Optical is on the left side. The right side is the UV. I didn't have, I thought that I'm just running out of time. I just stopped it. So all the right sides are optical. You can see that it's so bright, but when you change to ultraviolet, there you see only a handful of stars, much less, and you can even resolve the central cores of these clusters. Basically, you are dimming the low mass stars are very dim. You won't detect them, but the spectroscopy is possible, which is basically like a slitless. There's no slit, so you have a grating, and then instead of the single star, you will get the spectrum like this. The light gets dispersed, and instead of a point, you will get a line that is a dispersed flux. That is a spectrum. But that is a very low resolution, and there is no slit. So if it is a very bright object, isolated object, it is possible. So there
Yeah,
are
I'm
a few
asking
papers
for
which have come out. You can look into it.
I am asking regarding the quasar spectroscopy, madam. Seyfert galaxies and quasars.
Yes, so if you have quasars with broad lines,
yeah, they have.
and you would be able to, you can do that, and you need to know if you what kind of lines you expect there, because there is no you don't have a line spectrum, lab spectrum to compare with. Like when you do from ground-based spectroscopy, you normally what you do is you do not know what wavelength the line comes in, right? So you will take a lab source like a helium neon laboratory source, you know what lines correspond to which wavelength, right? So that is not there. So you should know the previously a priori what lines you're expecting. And if they are redshifted, the lines will also shift.
Yeah, H beta and O3, they are the strong lines, madam. In
This is
AGN.
UV. H beta
Yeah,
and
I mean
UV are in the
for high redshift that will come in. I mean, so you
no
can.
high redshift. Those will go to infrared.
Yes, madam. Yeah.
This is UV.
Yeah, madam. What about Astrosat 2 plans? You are involved. I think some meetings are going on.
Yeah. So there was a call from the Indian Space Research Organization. I don't quite remember the year, maybe 2017 or early 18. So we submitted a proposal for the next UV mission, which is a 1 meter class telescope, which will have an imaging resolution similar to HST, because this you can see that this resolution is coming at about 1.3 arcseconds, which is not very, very, very good. We are looking at a 0.2 arcsecond resolution.
Yeah.
And we submitted a proposal, and for multi-imaging, or rather simultaneous imaging in ultraviolet, U band and G band, and spectroscopy and multi-object spectroscopy. The idea is that the central regions of these clusters, you can actually get their spectra, resolve them and get their spectra. Similarly, you can see these galaxy out here. You can actually resolve individual knots over here in this galaxy and take spectrum to find out what is the chemistry they have, what is the velocity, why they are having star formation there. So this is the plan, and this was kind of cleared for a pre-project phase based on its maturity in end of 2018. And for the last 2 years, we are in the pre-project phase, and we are almost done with the final design of the optical design. And we have to have a discussion with the mission to finalize the the full details regarding weight, the total volume, etc. And we are looking forward to have a collaboration with Canada in this project. Yeah, it is in the pre-project phase. It's not yet approved, but we are working hard to complete the project DPR.
So how long Astrosat will perform, madam, better?
What we hear from ISRO is that it'll continue to work, and all the instruments, including UV and the other X-rays, are going satisfactorily. Right now, the far UV detector is working extremely fine. As a calibration scientist, I also monitor its health and the sensitivity. The sensitivity continues to be the same as from the day one. It is not deteriorated at all. So that's a very good news. So we hope it will continue for a couple of more years, definitely. And they think that they still have fuel and no problems with respect to the spacecraft and the bus things, where you have to make them properly, shift them into the orbit, right? So it has to be stable. So they also have no problem with stabilizing the satellite. So it should continue for a couple of more years.
Yeah, thank you very much, madam. Thank you.
Ma'am, there is one more question.
Yep.
How do stars die? Do they emit lot of energy in the process?
Yeah, so stars die I didn't have a slide on that, but different types of stars die differently, but it is decided by its mass. So once we know its mass, we can actually say how it will die. Because if it's a very massive star, it will die as a supernovae, leaving a remnant. Either it could be a black hole or a neutron star. A lesser mass stars will die with a remnant as a white dwarf, but the material around it will be dispersed and they pollute. And sun-like stars will die with a planet like a planetary nebulae with a nebular phase and a white dwarf. Some of the stars like the brown dwarfs, which are just a little hot, they just stay there. They won't be. They just cool down. That's it. We understand it, and a lot of material is available in the internet for reading on these.
Ma'am, how can we measure the lifetime of stars?
Yeah, it's a very good question. We don't live long enough to measure their lifetimes, of course. Yeah, so we actually study something called we look at different types of stars, and we create models, and we have snapshots. Though we don't live, but there are stars of various ages available, right? So you take snapshots of all this and create a model and try to fit it. So that is how we estimate their lifetimes. And comparing the observations with models. I think Krishnamurti is.
Yeah, madam. Yeah, madam. So good morning, madam. So nice of you. So it's a very wonderful and interesting talk, madam. Very, connected to our topic of a conference, International Science Fiction Conference. Here, my question, I have a question. How the stars are forming, new stars are forming. So is it that due to the physical, changes within the stars, which make into make for the generation of new stars, or is just our internal collisions or something, reactions between, interaction between the stars, it may make to generate new star. So that is my question.
Yeah. So So your question is, I mean, I understand. I just put it together that you have two stars. They create somehow the third star, or you actually start from scratch. Okay. We do, I mean, what we understand is we do start from scratch. So what actually happens is you have huge clouds of hydrogen, huge amount of clouds of hydrogen. In the first picture I showed, you could see the the kind of a reptile kind of a thing, right? So you could see the dark patches in the sky. So these dark patches are nothing but the huge clouds of hydrogen. So what we understand now is that inside these clouds is very, very cold, extremely cold. and these cold conditions allow them to form molecules. So we have molecules, and they are sustained this cloud because of thermal pressure. So their internal temperature keeps the thermal pressure, so that is sustained against gravity. But when they cool down, they can actually have molecular emissions and things like that, and they eventually cool down. When they cool down, the gravity they are not able to support. So there's a huge amount of clouds, and they at some point they are not able to support their own weight and the gravity. So all the objects, I should tell you, in the astronomy are fighting against gravity, either by going around in circles or having temperature. So if the temperature reduces, the gravity takes over and then starts to collapse. And then during the collapse, it heats up, they again collapse, it heats up, again collapse, and then finally it goes to the stage where the internal interior goes to about 1,000,000 degrees, where it can start generating its own energy, and that energy stops the infall. So throughout the lifetime of the star, it's a battle between the energy generation and gravity. Throughout its life, it's the battle. So finally, the gravity wins. When the energy production cannot happen, the gravity wins and settles down into a remnant. So that is what actually happens.
Thank you, madam. So nice. Yes, madam. Malvika?
Ma'am, are the shock waves generated by a supernova electromagnetic in nature?
Electromagnetic in nature. No, shocks are normally pressure waves, right? So it's basically, yeah. So the electromagnetic radiation actually ionizes, so pressure waves are different. So, okay, that reminded me that during the collapse of the clouds, you can actually, some supernova explosion can also give an external pressure to the cloud, which can actually compress, and the shock compression can start the star formation. You also see preferential star formation in spiral arms of a galaxy. There's a spiral wave is there. So that compression happens. So you can have external compression, which can accelerate the star formation. Yeah, coming to shock wave, it's a pressure wave. It's not a electromagnetic radiation.
Thank you, ma'am. Thank you for this wonderful session on a very relevant topic to our conference. I now request Professor Vijay Kumar H. Dodmani, sir, Head of the Department Physics, Penn University, to propose the vote of thanks. Over to you, sir.
I thank Professor Annamalai Subramaniam Madam for kindly accepting our invitation and delivering very, very interesting talk. And she spared her very precious time and accepted our invitation. And I thank you very much, Madam, for sparing your time and delivering the talk. It's nice of you, kind of you, Madam. Thank you very much.
Yeah, thank you so much for the invitation. I hope you could take some.
You are very busy. Despite in very last week, I tried to contact you and I accepted my talk invitation, and I am very thankful to you, Madam. Thank you very much.
Thank you. Yeah.
Thank you, Madam, from the Department of Physics side.
Yeah. Thank you.
So, Malavika?
Yes, sir. Yeah. I now request all the participants to join their parallel sessions.
Okay. Thank you, Malavika, for holding the sessions excellently, and we will get back to you soon.
Yes, sir.
So, Chairman, sir,
thank you,
and the convener, we will switch over to our channels, respective channels. We will be back.
Thank you,
one and all.
Yeah.
Sure.
Sir, ಇವತ್ತಿನ ಕಾಮನ್ ಸೆಷನ್ ಮುಗೀತಲ್ವಾ ಸರ್?
ಕಾಮನ್ ಸೆಷನ್ ಮುಗೀತು ಮಾಳವಿಕಾ. ಥ್ಯಾಂಕ್ ಯು ಸೋ ಮಚ್.
ಸೊ ಪ್ರೊಫೆಸರ್ ಕೃಷ್ಣಮೂರ್ತಿ ಅವರೇ,
ಸರ್
ಸ್ವಲ್ಪ ಮಾತಾಡ್ಬೇಕು. ನಾಳೆ ಸ್ಪೀಕರ್ ಪ್ಲೆನರಿ ಸೆಷನ್ ಟಾಕ್ ಸೂರ್ಯಪ್ರಕಾಶ್ ಅವ್ರ ಟೈಮು